So we have seen, we have defined segregate classes and looked at some basic properties. So today the objective is to maybe get some understanding of what they're supposed to do. So first we'll prove the result that I had mentioned last time. So let me quickly recall the definition of segregate classes of a scheme. So Y is a scheme, and X in Y is a closed subscheme. So then we defined the segregate class of X in Y to be, so this is not an operator as we had constructed for vector bundles. This is just going to be a class, and we talked about why we have to do it that way. So here so let P be the projection from the projective completion of the normal cone to X, and then what is this? This is P lower star of the sum I greater than or equal to 0 of the, so you take the Chern class of O1 to the power I and cap with the fundamental class of this CXY plus 1. Okay, so and then then ultimately you push everything forward to X. So this is sitting inside the Chow ring of X. So I also mentioned that see this plus 1 thing is only because the cone may be empty sometimes, right? So just to avoid situations like that, but usually that will not happen. So if all components of CXY, the projective cone of CXY, or projectivization of CXY are non-empty, then SXY is equal to Q lower star. So Q is now the projection from just the normal projectivization of the normal cone to X of C1, C of O1. Okay, sorry. Summation I equal to 0, C1 of O1 to the power I, capped with fundamental class of CXY. So okay, so that is the definition, and we also proved that. So we proved that if Y is equal to so let me see, yeah, Y is if Y is pure dimensional, with components Yi, so the multiplicity of Y at Yi equal to Mi, and if X this is X in Y is closed, and Xi is equal to X intersection Yi, then the segregate class of X in Y, you could basically reduce the problem to computing on each component. So this ends up being summation over all I of Mi S of Xi comma Yi. This is what we had done last time, and now I'm basically going to talk about how these things behave with respect to proper push forward and flat pull back. So here let Y prime to y be a morphism of pure dimensional schemes. Yeah, I should name this, yeah, f is this, x in y is closed, x prime is equal to f inverse of x, and g is equal to f restricted to f inverse of x. So okay, to x prime, this is going from x prime to x. So you have okay, you have a square of these things. Anyway, I'll draw that square later. So then, if f is proper, so that we can talk about the push forward, then we want to see, and okay, so we take y to be irreducible, and f, yeah, f also maps, f maps all components of y prime onto y. Then so if you take the push forward of, so see, the Segre class actually sits on Segre class of y prime at x prime actually just sits in x prime, right? I mean, it's supported on x prime. So I'll just push forward along g, right? So that's the same as pushing forward along f, but it's just a matter of notation. So g lower star of s of x prime y prime, this is equal to the degree of y prime over y times s of x comma y. So we'll have to clarify what we mean by this degree. I will say that in a minute. So but anyway, I mean, it's a fairly neat statement. And for flatness, so if f is flat, the statement is even simpler, that then g upper star of s of xy, this is equal to s of x prime y prime. Okay, so what do I mean by the degree? So if y prime has components y1 prime, so on up to say yr prime, then the degree of y prime over y is to be defined as the summation over I. So what you would want to do is degree of well, y prime over y prime I over y, but then you also have to multiply by the multiplicity of y prime at yi prime. Okay, so maybe we'll just take y to be reduced for now. Okay, we'll see if we need it, if there is a way to at least in the book this is not part of the hypothesis, but maybe it is necessary. We'll think about it. Okay, so the proof is quite mechanical actually. So proof, so you replace, so first using the previous lemma, we may assume that well, we may reduce to the case where y prime is also irreducible. It's irreducible. Yeah, I think you may be right. I mean, it may be we may need to have y reduced to formulate this properly like this. Anyway, we'll see later. Okay, so then we have this kind of so we'll define m of so this was the kind of notation that we had when we constructed the deformation scheme. This is the blow up of y cross p1 at x cross 0 or x cross infinity, whichever. So this is a construction we can do for any closed immersion. So we will do it for both these pairs. So we have this. So let's see. So I have got m of p of c x prime y prime plus 1 and then this yeah, so this there's a map of m x prime y prime going like this, and this is mapped onto x prime, and then this maps down here to m x y. Here you have p of c x y plus 1. Okay, and this is a Cartesian square, and so here also you have x. This is also Cartesian. And so let us label these maps. We'll call this one capital F, this is capital G, this is little g. Let's call this one Q, and this is Q prime. So this is what I had written here. So let me, sorry, yeah, exactly. This is, this is a closed immersion, yeah. Yeah, I thought I'd make, yeah, now it is okay. Okay, so anyway, so now this is all about working out things on this particular square. So let d equal to the degree of y prime over y. So then, yeah, so let me call, just for short, write a little bit of short form, let me call this as m prime, and we'll write this as m. So, okay, maybe I'll just, m is mxy, c is cxy, m prime is equal to x prime, y prime, c prime is equal to c x prime, y prime. Okay, so f of f lower star of m prime, this is equal to d times m. Okay, well, so yeah, let me just say, this, oh no, this was fine, but so now, for E. So yeah, as I had written here, f lower star of m prime is equal to d times m. And now let us just write out this calculation. So here this g lower star of m prime of p of c prime plus 1, this will also be equal to d times p of c plus 1. Okay, so this requires that, well, as I said, that whole, this will require that lemma probably that no, this will not require anything. No, this is fine. Yeah, this doesn't require anything special. So, yeah, this is just because this is equal to G lower star of, okay, I'll write it like this. This is just G lower star of G upper star of G upper star of C plus 1. So this is equal to D of C plus 1. So G prime, no, what do I want to do? I want to do G lower prime of S of X prime Y prime. So then you write out the formula for this G lower star. So what is S? So what? Okay, it's going to be Q prime lower star of the sum over I of C1 O of G of, okay, so one thing is that, observe that G upper star of O1, of this P C plus 1, right? So this is just the same as O of P C prime plus 1 of 1. Okay, so I can just so that's what I have here. G this is just the pullback of the line bundle. So G upper star of 1. Okay, so I P of C plus 1.
Okay, you are defining it to be P of C direction.
What is that?
What is
Of which one? See, you're talking about this thing, but well, this is actually equal to this, right?
No, what is G?
Yeah, that's a good point. Yeah, 1 second. Yeah, maybe I have to think about that. Yeah. Yeah, it shouldn't require this. Yeah. I don't. Yeah, this is, I shouldn't have done actually. It's just this is just from definitions actually. P of C plus 1. Right? Because it's a surjective map, and so this is all. You just have to take the degree. Right? So. Yeah. So okay. Yeah. So. But anyway, I mean, so yeah, that's not an issue here. So I take this and I intersect with P of C prime plus 1. Okay, so it is like this, right? So we are going which way? So first we are going this way, and then we are going this way. We could go this way instead. So this is equal to Q lower star of G lower star of sum of C1 G lower star O1. Okay, so now we can use the projection formula for this. So this is Q lower star of the sum over I of C1. So this is the line bundle below. This is okay. One second. This was C prime. Yeah. So this is a class upstairs. I'm taking this, having this the churn class of this pullback bundle acting on this class. So that is the same thing as just taking the churn class of the original line bundle downstairs and then acting with it on the push forward of this this class, right? So this is going to be O1. So I'm not writing O of what. I think it should be clear now from the context. Intersected with D times P C plus 1. Okay, and then this is equal to just, so this is exactly the definition of, I mean, if I pull this D out, I get exactly the Segre class downstairs. So it's very, very mechanical. Okay, and now let us look at the proof of, so for B, suppose F is flat. So then this is much simpler. This is G upper star of S of X, X comma Y. This is equal to G upper star of Q lower star of summation I of C1 of O1 to the I cap P of class of P of C plus 1. Okay, and then this is equal to, so which way is this? So we are first pushing forward along this and then pulling back along this. So that could be the same as pulling back here and then pushing forward like this. So this is Q prime of Q prime lower star of G upper star of summation C1 of O1 I intersected with P C plus 1. And now here the way this is evaluated is even simpler. Then this is just you apply G upper star to both these things. So summation over I of G upper star of one the churn class of this, the I intersected with P of C prime plus 1. Which is equal to, okay, this is equal to S of X prime Y prime. Okay, so this is very straightforward. Yeah, any questions about this proof? Okay, so an immediate corollary is that, well, something nice happens when F is proper birational, so like a blow up. So then basically what we are saying, then this degree is 1, and so we are just saying that along a proper birational map, the Segre class pushes forward to the corresponding Segre class downstairs. So that is called the birational invariance of the Segre class. So let us make use of that for doing a calculation, an explicit calculation which gives us the Segre class. So let X be a closed subscheme, proper closed subscheme. Y. So here, yeah, let's take Y to be a variety. So yeah, I mean, I think it should be possible to formulate all this even when y is not reduced. Though I mean, I suppose it has to be written a little more carefully. Okay, so let y tilde be equal to the blow up of x at of y at x, and let so that you have this pi from y tilde to y, and let x tilde be the exceptional divisor, and you have this map eta, which is pi is equal to pi restricted to x tilde going from x tilde to x. So then the Segre class of x in y can simply be written as the summation of k greater than or equal to 1 of eta, so of minus 1 to the power k minus 1 of eta lower star of x tilde to the power k, which is the same as the summation over so again this should be k greater than or equal to 1, I guess, of eta lower star of c1 of O1 to the power k cap with p of cxy. Okay, let me just check that this is correct. Yeah, seems okay. So see, yeah, this is fine. Okay, so proof. So one thing. X tilde is a divisor, right? So I can just take the intersection of the divisor with itself. Okay, so yeah, so how do you think we should prove this? So I mean, yeah, this seems kind of familiar, but let's just talk about the first one. How do you get there? Well, PC, so this is actually x tilde, isn't it?
Yeah, x tilde.
But so, okay, what is, I mean, our Segre class is written in terms of O1, right? Of that particular projective morphism. What is x tilde? How can you write in terms of x tilde? Yeah, O of y tilde, x tilde, this is equal to O of minus 1 of this blow up. Right? So, blow up of, okay, so that is what it is, right? So why is that? Because I mean, what happens when you blow up is that the ideal that you blew up, it upstairs it turns into O1, right? So so if the ideal is O1, then OX is going to be OX tilde is going to be O minus 1, and so C1 of O1 dot alpha is going to be equal to minus x tilde dot alpha for any class alpha. So the sum here starts from so I'm going to have I'm going to have all these minus signs. The sum here starts from I mean it was starting from 0, but now I'm starting it from 1, because the first time you intersect you intersect this this PC plus 1, Cx plus 1, and you intersect it with O1, then you first end up with x tilde. Right? So the series starts with x tilde. Okay? So it's just this, using this to rearrange, rewrite the expression. But yeah, I mean, this is now looking very nice, right? It looks like a very nice expression. But okay, so these are, this is just a formula that you can use to. Okay, so what you have is summation k greater than or equal to 0 with C of O minus 1 to the O1 to the power k capped with P C plus 1, and then you are pushing this forward. So okay, one thing is that I could just do this PC. No, that is not what I want to do. PCX y plus 1. Yeah, that's a good point. Actually, I mean, the expression is correct. It's just, I think, let me think about the explanation. Yeah, sorry. Actually, this is, I could just do it like this, which is, I mean, I have to do this because I have not really set up the I'm not using the deformation scheme here at all. I'm actually using this formula, pi lower star. Right, so this is already x tilde. It starts, so it's when k equal to 0, I actually already have x tilde. Right, this is actually the class of x tilde. So this is equal to so pi lower star of x tilde minus, so plus the Chern class of O1 capped with x tilde and plus the Chern class of O1 squared capped with x tilde and so on. So this is what it is, and now replace all these by minus x tilde. Right, so this is equal to pi lower star of x tilde. Well, I'll just write x tilde now, not so x tilde plus minus x tilde times x tilde plus minus x tilde squared times x tilde. Right, that's what it is. So that's why there is the sign is off by 1. Yeah, we are using the theorem because no, are we not using it? Yeah, actually that is true. Yeah, we could. Yeah, that is true. We don't really need the theorem. That is also correct. Yeah, but we could also go upstairs and do the calculations. But yeah, that is fine. Okay. Yeah. So the thing is that this is just a formula. We still haven't really gotten a good feel for what the Segre class is supposed to do. So let's talk about a possible interpretations or degree of a projective scheme. So let me just remind you of what this is. So okay. Maybe I should have. Okay, I'll come come to, so it will be clear in a minute why I'm talking about this. So recall, so I'm just going to recall some material from that many of you may already know. This is from basic commutative algebra. So the references would be Atiyah MacDonald, and some of it is, some of what I'm going to say is just from the first chapter of Hartshorne. So if R is a graded ring, so I greater than equal to 0, graded commutative ring. So this is Noetherian graded ring. Say, and it is generated over R0 by R1. So this is set up in somewhat greater generality in Atiyah MacDonald, for example, but I will just say something in the simplest possible cases. So assume that, say, R0 is Artinian. So it could be a field, for instance, and now suppose M is Mn. So this is a finitely generated graded R module. So then if we consider this function, the function n going to the length of Mn, right? So what do we know about this function? That when n is sufficiently large, you can actually evaluate it by a polynomial, right? So this is given for n sufficiently large by a polynomial which I will denote by Hm. So this is the Hilbert polynomial of M, and Hm is a polynomial with rational coefficients. And so having some degree, degree, say I will write it as dm minus 1 for some integer dm, and this d has some meaning which we will which I will talk about only in the case of when M is actually the your ring. So now the thing is that when now let A be a local ring, with maximal ideal M. So then I can look at the graded ring A, which is the direct sum over I greater than or equal to 0 of M to the I by M to the I plus 1. So then I can apply this machinery to this, and then if you take if you define Hn, chi n equal to the summation of HA, H gr A of say I, where I is less than or equal to n. So this is this is supposed to be the dimension of A over M to the n plus 1. So this no, M to the n, M to the n. So this is a polynomial of degree So the thing is that the degree will be 1 more than the degree of H. So this will be D of GRA. Okay, and then there is this theorem in, for instance, in Atiyah McDonald chapter 11, which tells you what this is. So fact that D of A, this is equal to the dimension of A. Okay, so what does this have to do with dimension of over good point, over A mod N. Sorry, yeah, this should again be dimension. Yeah, no, what am I saying? No, what is wrong? Yeah, it is length, but yeah, okay. Yeah, sorry, let's say length. Yeah. Okay. So yeah. So this is the Krull dimension. Okay. So now we can also apply this. For variety, so K is a field, and let's say that S is the polynomial ring x1 up to xn. So then if Y is a projective variety, so okay, maybe I'll write this equal to this. This is contained in embedded. So it's a closed subvariety of proj S equal to Pn. So then Py, I define Py to be the Hilbert polynomial so I mean I just defined H to be the function, but Py is a polynomial that actually matches the function for large values. The Hilbert polynomial of the homogeneous coordinate ring of Y, of the So then there are a couple of results in Hartshorne which explain what this has to do with the geometry of Y. So let EY EY be the coefficient of so yeah, notice that the degree of this polynomial is 1 less than the Krull dimension of the homogeneous coordinate ring, right? So which is equal to exactly equal to the dimension of Y. So t to the power dimension Y by Y. So this is supposed to be the degree of Y. Okay, so so this is something that it's not an intrinsic property of Y; it's a property of Y, as sitting inside projective space. So now how do we see that? So if maybe I should say for this. So Okay, so if H is a hypersurface of degree D, okay, hypersurface cut out by a polynomial, by a homogeneous polynomial of degree D, then E of EH is equal to D. Okay, so this is Hartshorne chapter 1. And in fact, everything, I'm just recalling these things entirely from Hartshorne. So then also we know the following, that so theorem, so this is theorem 7.7 in Hartshorne chapter 1. So this is that if y is let's say y is a variety of dimension greater than or equal to 1 in Pn, and H is a hypersurface not containing y, then and suppose that Z1 up to Zs, these are irreducible components of y intersected with H, and if let's say that Mi is the geometric multiplicity of y intersection H at Zi, then he proves this result, that summation of Mi of E Zi, this is this sum over I, this is equal to E of y times E of H. Okay. So using this now, you can prove that using this you can prove that Ey is equal to the degree of okay, it is equal to the number of points of y intersected with say L, where L is a generic okay, since I don't really okay, it's fine. So y is a generic linear subspace of dimension n, of dimension n minus the dimension of y. Okay, so all I'm saying is, I mean, I'm not really writing down this very clearly, but what I'm saying is that this number that you get by this recipe is, it happens to be the degree that you would, normally define for a variety sitting inside projective space. Okay, so now what does this have to do with Segre classes? So I want to talk about how to define the multiplicity of multiplicity. At a subvariety. So let's say that y is a variety. Okay, why do I need it to be a variety? No, maybe not. Okay, let me say that y is a okay. Let's say that y is a variety and x is a subvariety. So as a simplest case, suppose simplest case is something that we started that I started in my first lecture, that y is a hypersurface given by hypersurface in AN given by f equal to 0. Okay, so f is some polynomial and x is equal to the origin. So then what should we so we multiplicity of y at x, how should we define this? Okay, maybe since I have also written geometric multiplicity, let me say, okay, multiplicity of y at x. How would you like to define this? So suppose you have a curve which looks like this, right? So what is this? This is y square is equal to x square minus x square plus x cube, right? So what is the multiplicity at this point? 2, right? So now more generally, okay, so this is y square minus x square minus x cube. So what we are looking at is this lowest degree part, right? This is something we focused on earlier. And so what is the property of what is the number that we are picking out of from this? This is the degree of that thing, right? So more generally, if I am talking about a hypersurface, what did we do? We focused on the lowest degree non-zero homogeneous component, right? Of f. And then does it seem reasonable to say that d should be the multiplicity at that point, right? This is equal to the degree of the lowest, lowest degree non-zero homogeneous component of f. Okay, so now so if f is equal to if f is equal to fd plus fd plus 1, so on. So we are focusing on this part, right? So can we describe this d more geometrically now? Yeah. Well, the degree of the tangent cone. So see, fd defines a hypersurface in P n minus 1, right? And d is equal to the degree of let's say hypersurface H is the degree of H in which is sitting inside P n minus 1, right? So you should remember that the degree is not an intrinsic property of the hypersurface. You should remember that it really is a property of the embedding. Okay, so then Well, we know how to calculate this, right? So, okay, there is this long complicated definition using Hilbert polynomials, which is something I only talked about because Anand may require it later. I don't need it. So what I really need is this particular definition. Okay, so can you, this is something you might write when you had just started learning algebraic geometry, right? Now that you have learned all this fancy stuff, what would you write over here? So you are intersecting with a linear space, right? Of a certain dimension n minus. So let's say that the dimension of y is r. So n minus r dimensional linear space can be written as the intersection of r hyperplanes, right? What is hyperplane? It's basically O1, right? So this is so what I mean by this is equal to so this is equal to O1 of P n minus 1. So I can take its Chern class and I cap the class of okay, maybe I should call this is cap the class of H, right? I take this and this is a certain number of points. Now what do I do to this this collection of points? I mean it's a zero cycle, right? Basically I have a zero cycle. I take the degree. What is actually degree? When I say what is the definition of degree? Yeah, but I mean a sort of a more sophisticated way of saying this is that this is equal to P lower star, where P is the map from Pn minus 1 to spec K. Right? So, so this should be, sorry, I should have written here n minus 1 minus the degree of, no, what am I saying? This should be, this is a hypersurface, so n minus 2 is what I should be saying, right? Now, do you see, does this look very familiar? Right? Isn't this exactly Segre class? So that's what Segre class is doing. Okay, so this is what you were doing. This is what you feel like doing at a point. Again, I mean, let's so slightly more complicated. So more generally. So let's say that y is a variety and P is a point of y. Okay, so let's say a closed point of y. Okay, let me put a question mark here. Should it be closed or not? Okay, so let's think closed for now. Okay, so then what do we want to do? We want to okay, let me actually say closed for now. And so this is a closed point of y. I want to talk about the multiplicity of y at P. This should be equal to what? I should just write down what I did over here, right? So I should just write down P, okay, sub variety in say AN. Okay, we're still talking about something quite concrete. Okay, maybe I don't particularly need this at this point. I should be able to do without this. So I should say what P lower star is. Okay, I will say what it is in a minute. So this should be what? This should be C1 of O of P C P y, right? 1. And then how many times do I need to take the intersection? So I'm going to intersect what? I'm going to intersect P C P y, right? So whatever is the dimension of this, right? So this is equal to, so what is the dimension of this? Let's just write whatever it is. So dimension of P of okay, where P yeah, so now this is going to be P is going from P CPY to spec of okay, maybe I will even say something simpler, k valued point. Okay, or maybe not, just let me just say closed point, and then this is actually going to the point spec of kappa y, where this is the residue field at y, right? So now can we write so again this is the Segre class, right? So now more generally, yeah, okay, I should say P here, right? Is that enough? That is okay. This is capital P. Yeah, maybe yeah, I could turn this into pi. So even more generally, so now I want, so what is more general now? So I mean this same, so this works at any variety as long as I'm taking the multiplicity at a point. Now if I want to talk about multiplicity at a sub-variety, what should I do? This is a little more subtle problem, because let us look at something like this, that there is a cone, okay? So this is my y, and then I just take a line along the cone, and that is this is my x, and now I want to talk about the multiplicity. What should I do? See, the thing is that at most points except for this one, this is all quite nice, right? It's just a smooth thing. So then the multiplicity should just be 1. But then something funny is happening at this point. So it means that when I talk about multiplicity at a sub-variety, I need to talk about it in a more sophisticated manner. I need to keep track of where I'm talking about it, right? On the entire sub-variety. But still, if I wanted to talk about just the multiplicity at x, what should I do? I should focus at the generic point of x, right? So, okay, so from this, it seems that the multiplicity, so if y is a variety and x contained in y is a closed subvariety, the multiplicity of y at x should be equal to, well, what should I do? I should really do the calculation, this whole calculation, just using, so instead of using, so this, what do? I take the normal cone of y at x, right? And when I do this entire calculation of the Segre class, where do I end up? I end up on x, right? I get a class on x, but do I really care about the whole thing? No, I only should be looking at what is happening at the generic point, right? So this should be equal to, well, the Segre class, well, yes, the Segre class of the Segre class S y x, okay, sorry, x s x y. So what should I say here? What I really mean is that I don't want to do this entire calculation. I really want to take the fiber of this picture over the generic point and then do the calculation, right? So so can you tell me what I should do here? So okay, that's an answer actually, right? I could do this entire calculation. I could take the fiber of the of this normal projectivized normal cone over the generic point and then do this and actually compute the Segre class there. But okay, but another way of saying this would be to say that, okay, and if I do that, what will I get? I will get a number, right? But here what am I going to get? The coefficient of x in S of xy, right? Yeah, I guess I didn't, right? Probably, I guess I. I did all this at closed subvarieties, right? So I mean, normal cone is defined at closed subvariety. But still, I mean, if P is not a closed point, then what I'm saying is you take the closure of P, do the calculation, and then take the fiber of the normalized of the projectivized cone over the generic point, and then do this. So then this seems reasonable, right? So okay, so then this is actually our definition. This could be a definition. So this is our definition. Okay, so yeah, I mean, this is our definition. That's it. Now the thing is that when I do this, so this is yeah. So I have got so let pi from P, let pi be the projection of projection P C x y to x, and now consider the fiber over the generic point x of x. Okay, so little x is the generic point of capital X. So then what I'm saying is that then the multiplicity okay, and yeah, so the multiplicity what I mean is that, so you have pi prime is the so you, okay, I've got this kind of picture. So P C x y to x to spec of kappa x, and this is my pi, and then this is so there is something over here. So this let me call this P. Okay, I take this thing and let me call this as pi prime. So then so the multiplicity of y at x is just pi prime 0 star of so the thing is that P is projective over this, right? So I can talk about C1 of O1. So summation is sorry, is the yeah, this is fine I cap with P. So this is in A0 of spec of X, right, which is 2. Yeah, so the reason why I wrote it out like this is that now this entire calculation that I have done, see, now this is just, P is just a projective variety. So P is a projective variety, projective scheme defined over the field kappa x. I could just forget about everything else, right? The context of this, I could forget where everything came from. This is just something like this. Now, what I could do is ask for, so its degree. So its degree is is obtained from the leading coefficient of the Hilbert polynomial Hilbert polynomial, well, actually, okay, fine, which is equal to the Hilbert polynomial of what? So what is the see, the way I defined Cxy, what was it? It was the sum of I mod I to the j mod I to the power j plus 1, where I is the ideal defining ideal defining x. So this is equal to Hilbert polynomial of, so when I localize over here at the generic point, what do I get? I get the graded ring of what do I want to say? Oyx. Okay, I think some people write this the other way, but this is what I prefer. Right? So, so what this means? So, we could take the ring A equal to Oyx and define the multiplicity of y at x to be well, we could define it to be codimension y, codimension of y at x. Okay, I don't know how to write this y. Okay, y at x. So this factorial times the leading coefficient of the polynomial, giving giving n goes to the length of a mod m to the n, where m is the maximal ideal. So this is another definition of multiplicity. So we have basically shown that this is the same as the one that you get from the from this one. Okay. So this is the way to think about Segre class, that it's actually a sophisticated device to keep track of multiplicity at a subvariety. So if you just pick this number, you're actually picking out something very crude. You're only picking out what is happening at the generic point. But at other points, something more interesting may be happening. So that there you have to see then the parts of the Segre class that are supported at that particular point. Okay, so that is the way to think about the Segre class.
Why are these three characters?
Okay, I mean that was basically okay. So so given a projective variety, you can define its multiplicity in two ways. One is using the Hilbert polynomial, right, which is this one, which is where this comes in, and the other way is to actually show that you can compute it by taking the intersection of the projective variety with some linear subspace, right? So the Segre class thing is giving us that computation, that is coming from that interpretation, and the fact that those two approaches are equivalent, that is basically proved in Hartshorne. So I'm relying on that. Okay, so we can stop here.